So in this part, we will look into how virtual address or rather space is allocated to a process by the operating system. So the simple way in which operating system can allocate space to a process is to do static allocation. That means whenever a process starts running, just create page table entries for the entire virtual address space and assign corresponding physical pages to each virtual page, right? However, this is very inefficient. The thing is, most of the processes, they don't use the entire virtual address space. Okay, so for instance, imagine that you are running a simple hello world program. You will not be using the entire like 3 GB or 4 GB of your virtual address space, right? So you may be using maybe 1 byte or maybe 1 page of the virtual address space. In that case, doing static allocation of the entire virtual address is very inefficient. So what's the solution for this? Simple, dynamic, request based. Basically, do not allocate virtual address unless it is requested by the process. So here what happens is when we run a program, so operating system allocates space in the virtual address or rather create page table entries for only those regions that are as dictated by the program binary. Okay, as we saw in previous lectures, that compiler generates binary and it has virtual addresses for each section. So when operating system gets such a binary, it actually creates page table entries for only those regions and it loads corresponding content from the binary into physical pages, and then it updates the virtual uh, it updates the page table entries to point to those physical pages. Okay, and rest of the virtual address space is unallocated. That means rest of the virtual address, like if a process tries to access virtual address that is not present uh, in the program binary, like that is not present in the segments, then you will get segmentation fault. Like operating system just kills the process because operating system doesn't even create page table entries for those virtual addresses which are not explicitly requested by the process. So in order to access a virtual address, operating a process needs to ask the operating system to create those virtual uh, to create those entries in the page table. Okay, that means op- uh, a process has to ask the operating system to create page table entries for certain virtual addresses that it wants to access. So to do this, operating system provides most of the operating systems provides a system call in Linux kernel. It's called brk system call. So this system call actually, when a process makes the system call, this is when operating system just allocates one free page in the virtual address space and it returns that particular virtual address. So you can actually see this in your program when you are running. So when you want to access some memory apart from stack variables, so you actually use malloc and free, right? So malloc and free, they internally use this break system call. So what happens is when an application makes malloc uh, function in libc, so malloc actually calls break system call. Okay, break system call will allocate a page. Operating system will just allocate a page in heap region and it'll create a particular it creates a page table entry for that particular page and it returns the corresponding virtual address. Okay, and later when actually the process tries to use it, that's when the page gets created. It's called page fault. We will look in next chapter how page faults are handled, but for now just imagine that whenever a break system call is called, operating system actually creates a page table entry for one of the free pages in the virtual address space. User process actually can also use other system calls such as memmap to create virtual address, to create page table entries at arbitrary virtual addresses. Okay, so break returns a free virtual address, virtual page. Whereas if a process wants to have a specific address, if it wants to uh, map certain memory region at a specific virtual address, then you can use a map system call. So in the next part, we will be looking into the number 4, the page fault, basically how operating system manages physical memory. Basically, when we actually tries to access the page that belongs to that belongs to our virtual address, how operating system manages the pages. Thank you.